Hello, everyone. We are back to talk about the Wolfram Quantum Framework. So as you can see here, and you should be seeing in the stream chat, there'll be a link to this page where you can see some things. So if we scroll down just a little bit, you can see some examples of quantum circuits that you might want to create as part of working with the quantum framework. Another thing to draw people's attention to, if we look at the bottom of that page, are if you want to work with other frameworks. So for example, you want to do something in the Wolfram quantum framework and then work with either Qiskit or Bracket, or then send some kind of request to a piece of physical hardware to check the experimental result with what you're getting for theory. There are some links to examples of how to do those sorts of things on that page too. So today we have people who work on the Wolfram Quantum Framework, and so Nick and Mads, I'll let you introduce yourselves, and we can jump right into talking about some of the new functionality that is, I think, developed since the last time we talked about this about a year ago.
Thank you, John. Hello everyone. Mads Barami here. I'm manager of academic innovation team at Wolfram Research, and one of the projects that we are handling is our Wolfram Quantum Framework. And we were very lucky to have Nick as a developer of this framework. So Nick, go ahead.
Well, as you already said, I'm the main developer of this framework, so I'm just eager to share it with you, the new functionalities that we have, and all the ideas on how it works, and answer all the potential questions that can arise.
Yeah.
And as always, if you do have questions about anything we're talking about, feel free to put them in chat, because we do get to see those questions and respond to them. So before we get to talking about some of the new functionality, I'm curious, are there examples of that made it to that main page, or are they still, you have to go deeper into the documentation to find these?
So people, they can go to our documentation page. Basically, I think Nick, if you go to your notebook, so when they install, I think the best workflow would be on the notebook. Of course, this is the same on cloud, but from a mathematical notebook, after installing the packlet, which is basically those two lines of code, they have a long list of functionalities, and almost all of them, with the exception of a few, some very specific ones that are kind of still in progress, they do not have the documentation, but almost all of them, they have very detailed documentation. So that's how they can go after the documentation. But we will try to add more and more. And the workflow for us for development is very similar to the rest of functionalities in Wolfram Language. Basically, we do our best to make our code readable. So if they just look at the code and just read it, everything should looks very familiar.
Speaking of which, we also have a link to a GitHub repository where you'll see all the Wolfram Language code that's used to implement the quantum framework. And so you should now also be seeing that here pretty soon into the YouTube chat. And so if you're not familiar with GitHub, you can submit pull requests to locally download any code that's there. And then Nick and Mads, do you want to talk about what the process would be if people want to implement something that, let's say they have an idea for, oh, this would be a really nice named circuit to have, and the team hasn't gotten to it yet. What would the process be if people want to contribute those sorts of things?
Definitely, we highly motivate our users, to contribute. It will just go through a review process, and making sure it's kind of there's a peaceful marriage with the rest of functionalities that we have in Wolfram Language. By all means, we will add it to our framework. So we highly invite everyone to contribute. This is the GitHub page of all of the functionalities, and behind the scene, all the codes, how Nick has done this magic of quantum computation, so they can get it from there. Even there is a folder, then notebooks, even for us, the scratch notebooks, whenever we do any exploration, kind of behind the scene, people, they can see how we would basically explore different ideas. And many of the notebooks there, you would see they have very bad structure, or it's, you see that there is a different version of going through the same topic. Yeah, it's a mess, but again, we just put it there because people, they might want to see how we do all the development. So it's there. Besides GitHub, for any packlet, our users, they should know that any packlet, even if it's not on GitHub, after installing the packlet, you have all the codes on your end. So basically, like, you just need to go to the folder that the packlet object has been installed, and you can look into all the, like, basically documentation. Like, you see here, like, Nick is showing, like, the link on his end. And like, if you go to that directory, you can look at everything, all the code. So basically, like, in a sense, like, it's like, all the sources and everything is open, and you can look at, like, how all those developments are done.
And there are also functions for being able to find files and things like that. So let's say that you know the name of a packlet, but you don't necessarily know where on your machine it's located. There are functions that can help with that, that can help you find the absolute path to get there. So that is definitely worth mentioning. As far as some of these new features, you also have mentioned that at other points. So once you've installed this packlet, there are new features that are being developed. So if people are wanting to keep up to date with the latest features or even experimental features, is there a special link that they should go to get the dev version as compared to the stable version, which is in the packlet repository?
So, like, there's another, like, what Nick is showing, like, here, like, there is another link to install our packlet, which is basically, we call it, like, developer links. So that's the most updated one, like, the days and nights, like, me and Nick, like, we discuss, like, we update it, making sure, like, there is no bug or etc. Or if any of our users, like, if they report, like, any bug, like, we would take care of that immediately. So basically, that's the link that Nick is, evaluating right now. That's the basically, like, the development link, and you can install the latest one there. So, like, that's why, like, usually we recommend our users just go to that, like, development link, and, like, and download the packlet from there.
Awesome. And one last thing that people sometimes don't even realize you can do. So let's say that you've gotten the latest thing, and there's a new symbol that's been added that there isn't a documentation page for it because it's literally just been written. What can people do from within a notebook to find whatever symbols they have access to?
Like this.
Yeah.
Yeah. Yeah.
So it's a handy thing that people don't always realize you can do, right? Is once you've installed a packlet, right, all of the symbols are then there in the context that you can look up, and so that was question mark, and then Wolfram Quantum Framework backtick, and then whatever the regular expression is that you want to take a look at of what things are there. So if you are working with the versions that are even newer than what there's official documentation for, do remember that you can do that. Okay, so hopefully that's the basics of getting access to the latest stuff. So let's talk about some of these actual new features. So this is not the newest feature because it's been in there for a little while, but we didn't really talk about it last time that we talked about the quantum wave work, and that's tensor networks. So let's spend a moment to talk about tensor networks and what those are doing for us in terms of working with quantum computation. So as many of you know from, let's say, textbooks, you might have a density matrix representing the state that your system is in. But if you're working with very large matrices, this has a certain cost to it in terms of actually performing the arithmetic operations. And so there's various other formalisms you can use in order to buy yourself some not having to worry about large sparse matrices, let's say. So let's first talk about why tensor networks. What's the advantage of using this tensor network formalism, and how can they see these tensor networks in the quantum framework?
Well, the way you can see it is just the easiest way is just make any kind of quantum circuit, right? It has a quantum diagram, quantum computational diagram, and tensor network corresponds to each of those quantum circuits, and it can be constructed by just a single property, right? And underneath is just what we mean by tensor network is just a graph. It's an annotated graph which annotated with tensors and indices around those tensors, right? So this is just a usual graph object. You can ask whether it's a graph. It's going to say that it's a graph, and you can, if you want to work with it as a graph, you can do it. So all the familiar functionality on graphs would work with this kind of objects. Yeah. And in addition, we also supply a bunch of functionalities to work with these tensor networks, to like contracting them, maybe adding more tensors to them, turning them back to quantum circuits and all of that.
So one immediate thing people might want to know is you mentioned that the edges on this graph are representing what to contract. So let's say they want to actually see those contractions on the graph.
Yeah.
So these are being
So
stored as...
They're just tagged edges. So this is graph.
Mhm.
So in each graph, you can tag the edges. And what we do for this particular representation of the tensor network, we tag each edge with an actual indices that are being contracted. So it's like a pair of indices. Each of the pair corresponds to what the output index of the like the outgoing tensor, and what would be the input index of this ingoing tensor, right?
Mhm.
So if you extract those indices explicitly, you basically, this will tell you what indices would you contract in order to output the actual tensor that corresponds to the final result of the quantum circuit.
And then these can also be used as constructing arguments for doing the tensor contractions. Is that right?
Constructing arguments, but what you mean, maybe like constructing a path of your contraction, because it's not unique. What do you mean?
Gotcha.
Yeah. Yeah, right. Actually, I think I can show you. There's like this is it's an experimental thing, right? It's not going to work for everyone, unfortunately. But you can take the tensor network and you can just compute the contraction path of the tensor network. So hopefully it works. Yeah. So basically that would represent the list of not the indices, but the actual tensors, in single tensors or pair of tensors that you would just combine to contract all of the common indices between them. So if you do it in this particular order, you just actually will contract the whole network. And this computing this path is like a very complicated algorithm. It's not NP complete in general. It's just this is one is just a greedy algorithm that computes it, but there's some optimal ways of doing those too.
So I'm now curious to dive into that aspect a little bit further, right? So you mentioned that there's not a unique way of doing it. So what's picking out the way that's returned when you're doing this, as opposed to some other way?
Well, the result is going to be always the same. It's just the order of your contraction is going to be different, and the way you usually optimize this kind of computation of those paths is, for example, you can optimize for minimizing the size of intermediate tensors, or maybe minimizing the number of flops of the actual multiplication of numbers when you're contracting those tensors. So they're depending on what you want, and there is no good way of doing it in general, but you can do it in some way, in a greedy way, in an optimal way when you have a very small network, maybe. But usually, if you have a big one, the greedy way is the only way, is the only practical way of doing it.
So I also noticed there's a tensor network net graph. So what is the use case of that function in particular that is in there?
Well, net graph is, well, as you know, there's Wolfram has a nice neural network framework, right? Constructing neural network. This is also an experimental function that can turn any tensor network like this with a particular contraction path into the net graph object. But it's not going to be in general functional, but it can, I think I can see, can you show you this particular example? So tensor network graph, right? Net graph. If you just feed it this net and feed it this path, I haven't done it in a while. I'm not sure whether it would work. Yeah.
So this one is still experimental.
Yeah, but in general, it would just construct an actual. Oh, I'm forgetting something. The reason that it's not going to work directly is because neural network framework doesn't support complex numbers, and tensors in general do have complex amplitudes, right? That's a limitation of neural network framework, but we can kind of go around it with Actually, another feature that we also implemented recently is just, or improved it, not just implemented, is the phase space formulation of the quantum computation.
Ah, okay. So let's put a pin in that phase-space formalism. So we'll come back to that. We had another audience question, which was, so you in the argument to that first circuit you did, you put in Toffoli. So that's a named circuit. So can we back up for just a moment and briefly go over, so how can people see what named circuits are in there? And let's maybe see some examples of why having named circuits is helpful, so that you can save yourself a lot of typing for common circuits.
Yeah. So, but well, there's an autocomplete for all the named circuits that we implemented so far. So you can just see it like here. There's some private variable if you want to extract. Maybe it's somewhere. If you usually quantum circuit something names. Yeah, it lives somewhere in the packlet. It's not exported, but this is actually all the names. If you want to extract them programmatically for some reason.
So some of those, like, let me add one comment. Some of those, like, named operators, they are basically collection of gates that helps the users. It's like, for example, Toffoli or like, Bell or Magic. It's just a collection, okay? They don't take any other argument. So it makes your life easier. But some of them, like, behind the scene, they actually do some operation. For example, like, let's say that, like, you want to have the Grover search algorithm of a Boolean function, okay? So it's not an easy task. Actually, it's a very non-trivial task. You would say, like, given a Boolean function, what is the corresponding, basically, quantum circuit? And that's how, like, you can use it. You, like, as an input, you would say, like, give it any Boolean function. Here is like, and A and B and X or with C. And you see that's the corresponding circuit. So these family of, like, named circuits, they help a lot when you're building, like, any quantum algorithm. And we support, like, I can say, like, almost all famous, like, or common named operators, like all the family of Grover, Boolean, phase, Oracle, like, everything there. We support, like, basically the, like, Vazirani Oracle, like, it's a collection of basically, like, textbook examples that we support. And more than that, like, we also support, like, the graph, which is very common in, measurement-based quantum computing. Like, it's like you will not find it in any textbook. Like, so the idea here is that given a graph, whenever there is an edge, add a control Z between, like, those two vertices. Okay, so, like, that's basically the graph, and that's the corresponding, like, circuit. So those named circuits, it helps, like, a lot with, like, creating, relevant algorithms.
And so let's say that you're working with one of these named circuit algorithms, and you want to add a noise channel. So I know that we have the capacity to do that via, you can specify Krauss operators. Are there also sort of named schemes for including noise too?
Yeah, there's a bunch of built-in quantum channels. Those are basically used to implement noise or as models for noise. They act exactly as operators or other gates with a little bit of hidden feature that they're actually underneath. They're doing something more crazy than just acting on a wire and producing another wire. It's like we can show that. For example, if you make a quantum circuit with some kind of channel in it, bit flip, depolarizing, whatever. It has a nicer label looking thing. Can be symbolic, so this actual probability can be not just 1/2, but actually any integer probability. So if you make it into a diagram, but you also show the extra qubits thing, the extra qubits that come together with the channel, you can see that it looks something very similar to how we also show measurements. For example, I also add a measurement on a second qubit. See? So in that way, you can also see that channels act exactly at some kind of interaction with, in this case, environment. So this extra qubit or extra wire outputs you can think of it as an environment, but in case of measurement, you can think of it as this basically system that you have to trace over in order to actually get your probabilities or whatever. But as tensors and tensor networks, they act fundamentally in the same way.
And something I'm now curious about. So how much explicit control can you have over the properties of this environment? Is it just through the operators that you use to couple it, or are there other sort of parameters that you can set to, say, for example, the dimension of the Hilbert space that this environment is living in, or things like that?
Well, it's simply the set of cross operators or whatever define your channel is the way you control the environment. You can, in tensors, if you just forget about quantum computation altogether and you just think about how you do tensor index juggling or whatever, if you have a bunch of operators in form of matrices, if you stack them together, what do you get? You get a tensor with one additional index. So it's one rank higher than each individual matrix. And this is just what this output wire fundamentally represents. Is because you stacked a bunch of operators together and now you have more this additional output index. And we treat it as an environment that you fundamentally have to trace over in order to actually get to probabilities.
Okay, great. So so we've showed here an example. So aside from now specifying, we have some noise channel and we've done a measurement here. What are some of the other, if we want to run through, actually something I've seen that you showed before is, so if you take a look at these tensor networks and you do something as taking an operator and then the dagger of that operator composed with the operator, right? So what would that look like in terms of tensor networks, just for illustrating for people what the wires that aren't connected to anything, or I should more specifically say the edges that aren't connected to anything in these tensor networks. So these are representing ins and outs. So let's maybe take a concrete look at some of those.
Yeah, let's make one circuit that consists of just a state and its dagger, right? So in a circuit notation, it's just going to be a state looks like a gate without an input, and its conjugate is just something like that looks like a gate without an output, right? And if you just compose them together, you get something with no input and no output, and then that's just the number, right? So it's not a vector, not a matrix, it's just a single scalar. So if you actually take the circuit and evaluate it or contract the underlying tensor network. Actually, let's just take a look at the actual underlying tensor network. Right, it's just a single edge. So if this is a tensor, this is tensor. It's like in the graph, you don't see what are the free indices, right? But you also can extract the actual free indices, and in this case, there's going to be none, right? I think there's also a function for that. So this is the function, the network, and tensor network free indices is going to be an empty list. So there's no free indices. There's going to be a tensor of 0 rank. So if you contract it, you get a pure scalar, right? And in traditional form, just one. If that was, for example, for non-normalized or some actually different.
Yeah, let's pick a slightly more complicated operator here so we can see.
Yeah, well, if you just multiply it by 2, you get actually the scalar times 2. So this is not the actual one. This is the basis, one-dimensional basis notation for basis. It's like, yeah. So that's how we basically show one-dimensional basis notation.
Using the common terminology of quantum theory, like that circuit is basically the corresponding inner product. So like the inner product of like the first quantum state and the second quantum state, and those quantum states, they can be anything, as far as like of course, like you see like Nick is showing you the traditional form, like you see that looks nicer. So we are considering a trivial case when like it's, I don't know, like add a random like set or state maybe.
Too much parentheses. It's being added. Well, that should be the same.
Yeah. And in a sense, like this is kind of like how we should call it, a new interpretation, or like more semantic into the usual picture of like wires that we have in a quantum circuit operator. Because when people think like in conventional way about, like, for example, an operator, let's say like, we have Pauli X operator acting on second qubit. Nick, let's have a circuit and X goes to 2, for example.
Okay.
So like the way that like, people would see it is like, the normal interpretation is like this. They would say like, there is an operator, unitary, etc. It has some features, but it is acting on the second operator. But the way like, that the bare semantic would be like, this is an operation with the input, the second wire, the output is also the second wire. Okay. So why this interpretation is interesting? Because in our framework, you can change input and output. Okay, for example, like, Nick, like, as an output, give it, I don't know, let's make it to the first one. Like, it goes from the second one to the first one.
Do you want to like make a different operator or what?
No, like, the same Pauli X, but the output instead of like, you can do it with the Pauli X directly, but that one also like, let's do it with Pauli X without adding
It's gonna look ugly though, right?
Yes, but like,
because it's gonna make one. Yeah.
Still like, this is basically like, it gives the idea. So like, actually it's nice. It's not that much ugly, but anyhow, like, people, they get the idea. Like, these are like, what, let's call them unconventional basically approach, but like, this is truly like, what is happening behind the scene, and like, the freedom that you have. So this is also like, a quantum operation, but here like your input and output are different. And that's basically a very nice visualization for that concept of like, behind the scene, the tensors that we have. Like, look at the like, those two examples. Like, now it's Pauli X, it's the same Pauli X, but the input wire and the output wire, they are not the same.
So we're permuting the names of the indices, basically, right? You could think of it, as an abstract thing, or you could literally think of it as, you're hooking up, what you're measuring now under different names.
Yeah, you can think of this just like wire bending around.
Yeah.
That's why the string diagrams, you can think of those wires as strings, and they can bend all around, and you can represent not just quantum computation, but in general, all of the linear algebra. You don't have to restrict.
For example, like, let's look at a very famous, circuit that people have seen in the literature, and Bell circuit. Like, Bell circuit is a Hadamard and, C naught. Okay, so like, this is basically the textbook example that we have. Now, this is the same as having a cup. Okay, so like, now let's show you like, sort of like, minimal representation of that. So basically, like, these two
You
are
have the special operators that just render specially. It's like they're shown as just like wires, but underneath they are just as other tensors. They just rendered as a wire so that you can basically close your eyes and don't even see them. So in an actual computation, applying this circuit to the register, maybe it's kind of missing the some of the things here. If I do the 0, 0 on the left, like here, right? So all of this construction is equivalent to this guy. So if you construct this tensor network for this circuit and just take this operator that represents a wire, it's just and the wire is just a reshaped identity, so it doesn't matter which direction it's looking, it bends or whatever. It's just an identity, and that would be the same thing.
And so when we're using tensors to represent these things, and then we're intelligently picking what contractions we want to do in order to actually evaluate the outputs of these circuits, what's that buying for us computationally, right? Because I mean, the other way of doing it would be to just as the textbooks do, you just take some giant matrices, but of course this is horribly inefficient. So can you talk about some of the improvements you get by thinking about things as tensors?
Well, in a way we already mentioned it. It's like when we discussed the path of contraction, right? Because when you compute the path, all the intermediate tensors can be much less, much smaller in size. It's like if you just want to construct a tensor network naively, what we can do is just tensor product all the tensors there. Then in that way, you're going to be just very high rank tensor that you can't even fit in memory, right? But if you do it intelligently with some kind of particular order of contractions, all the intermediate results can be very small, but you get ultimately to the same result.
And so are there it would be interesting to see maybe in examples at some point somewhere some comparisons of what you would get if you did it, not the more intelligent way of making sure that your intermediate results are staying small. But anyway, that might be getting slightly far afield. So the basic point is that if you want to do things involving tensors, right, you don't want your computational load to grow, as 2 to the n as you're working with more qubits, right? That would be bad. And so if you're working with tensors and using some of these other methods of making sure that your overhead stays smaller, you can, in some situations at least, avoid having that bad situation happen where you're getting just an exponential overhead.
Yeah.
Okay.
So like if your intention not to compute the actual state vector that represents this giant tensor of size 2 to the n, but you actually want just maybe one scalar output as your result, your actual path of contraction is going to be very important.
Yeah.
There's going to be like hundreds of qubits, but you can still efficiently contract it classically to get a single number.
So another thing that is a new feature that has been added since last time we've done one of these are things to support the stabilizer formalism. Before we jump into stabilizer formalism, is there anything else about tensors that we haven't talked about yet that might be good for people to know?
No, it's not like we completely abandoning them. We're gonna come back to them in both stabilizer formalism and the rest.
Yeah.
So
like,
yeah.
If any comment, like, this way of thinking about, like, circuits and everything, like, it gives you lots of freedom to have, like, more generic operation. Okay. For example, let's say that, like, you would like to have an overlay of, like, basically 2 circuits. Okay. You would say, like, look, I have a copy, or I don't know, I have the complex of the same state, but instead of, like, looking at them as, like, 2 separate things, I would like just marries them on the top of overlapping, like, on the top of each other. And that's basically, like, what people usually, like, look at this case, like, you have 2 copy of, like, Bell, and you would say, like, look, each of those wires are 2-dimension and everything is the same. What if I just, like, the lower part, I just cut it and, overlay on the top of, the first part, and basically having an overlap? This is basically the concept of double. And notice, like, what is happening to the thickness of wires now. Like, maybe, like, Nick, if you show, like, diagram with, like, show wire dimensions. So you see here, like, now we go from, like, the wires that are 2-dimensional to the wires that are basically 4-dimensional. And this is, like, it's very handy because later on when we discuss about, for example, phase space and etc., like, for the phase space of, like, the quantum circuits, you need these constructs. Otherwise, like, you have to bang your head to the wall if you want to have the phase space representation of a quantum circuit.
Yeah.
So there's been a couple of things that people should make sure they pay attention to. So you can show wire dimensions, you can show the edge labels, which are just going to be the edge tags in those tensor networks. So there's several things like that if you want to see, in other words, there's extra data that's coming up when some of these visualizations are being shown. And so there are a few shortcuts like that to be able to quickly get those and not have to put them in yourselves, because there is extra data that's there. Okay, so yeah, let's go ahead and talk about the stabilizer formalism. So the stabilizer formalism comes up in quantum error correcting. And so I know that there's some new features that have been added related to that, where you can see generators that you might need in terms of being able to create various error correcting schemes. So let's take a look and see what sorts of things we have in there.
So the entry point to this thing is just a single superfunction, so super object that we have. So we call it tentatively as polystabilizer, but it can represent both stabilizers and Clifford operators, like in a single object. So it's still an experimental thing. I guess what should we start with showing?
Yeah, let's start with the quantum state. Like, what's the meaning of, like, stabilizers for a quantum state?
Yeah, there's some very greedy algorithms of how to actually turn a quantum state, if it's possible, to its stabilizer representation. I think it's loading something. Right. So this is the stabilizer object that represents this state, right? And I guess what you do focus on this thing, understand is that it contains a list of stabilizers, is that this thing is just a list of actual Pauli strings with potential sign, and it can also be presented by this tableau, which in full form is also includes destabilizers, but in this short form is just the stabilizers, right? And you can extract all the information about the state from this binary, just this bit matrix, basically, because it only will contain 0 and 1s.
And the other basic idea that maybe we should mention for people is that the stabilizers are going to commute with whatever you're wanting to go through the channel without having errors. And by virtue of this, you can construct a larger quantum circuit that has more physical qubits, or qubits, I suppose. But after you have got this physically larger thing, this is representing a smaller collection of logical qubits, so that after you get the thing out the other side, whoever you're sending the information to, if there was noise in there that is going to introduce operators that you didn't intend to be in that circuit, you can use this stabilizer formalism in order to try to figure out, well, what errors were introduced, so that then we can apply some corrections and get back to what we were meaning to logically send, rather than this larger collection of physical qubits.
Yeah, right. I guess we're not gonna talk too much about error correction application of this thing.
Okay.
Right, but we can just touch on some of the properties that it has. First of all, yes, you have to you can see that it's like if you increase the number of qubits, the nice thing about this representation, because this is the whole information that the underlying object contains, is this bit matrix. It instead of exponentially increasing in size, as would quantum amplitudes do, right? It just linearly increases in size. So it's in principle, it's very compact object. But the downside is just you can't do it for every state. So there's just some particular states that can be represented as a Pauli stabilizer, right? And states that do not are usually called magic states. So because they the underlying quantum computation with magic states can give you the universality, but without it, you can't do the universal quantum computation. So, but if you restrict yourself to just working with the states that can be represented as as this kind of objects, you can essentially do your quantum computation much more efficiently, even on classical computers. So if your quantum circuit is the one that contains only the Clifford operators, yes, I can also show that you can take some operators and also turn them into Pauli stabilizers like that. So they both can kind of have this dual nature. They can both represent either a Clifford operator or the stabilizer for a state. And if you have a circuit, if every operator within a circuit can be transformed to that, you can classically more efficiently simulate it to extract your measurements. So I guess that's the idea.
So, and as you mentioned, there's a somewhat greedy algorithm that goes into finding this representation. But then once you have this representation, what do you envision people doing with it here in the quantum framework?
Well, hopefully it's not going to be even visible to like usual user. It's like what we're planning to do at this point, I guess, is just have it as an additional method to constructing or just computing your circuits. It's like as soon as you can detect that your circuit is Clifford one, you can instead turn everything into Pauli stabilizer and classically simulate it much more efficiently. But we're also just experimenting that even for non-Clifford circuits, what kind of computation this kind of thing can allow you to do. It's like, for example, if it works, because it's well known that T operator, T gate, is not Clifford, so it can be represented as this, but you still can represent it as some kind of superposition of those. So, and because everything is symbolic in in the Wolfram language, you can just add them and represent it just as usual expression of those kind of objects with some amplitudes. And in general, you can do it for more complicated circuits, I guess, like the one that just showed above, like the Toffoli circuit. It contains a bunch of those non-Clifford T gates that can be represented. If you take this circuit and turn it into a stabilizer, what it's going to do, I think, I haven't done it in a while. It's just compile this whole state into just giant superposition of stabilizers instead. So this kind of object I personally haven't seen anywhere. So just this thing of thinking about superposition of states that your stabilizer states, right? So you can immediately say what it requires the magic states or not in order to construct it, or just you can simulate everything with a single one. So if you have this superposition, you can think of it that each of those individual one stabilizers you can simulate classically efficiently. But if you have a superposition and there are many of them, that's where your exponential complexity is coming from.
That's a quite interesting point. So yeah, okay. In terms of showing these generators that are going to be what you get that create the subgroup that is the stabilizer. You mentioned you can do this in. So what's the sort of most abstract way that you could represent these things as well? So here we've been doing it on specific circuits and states. So what's the most abstract sort of least connected to a circuit diagram way that's currently in the framework? Just out of curiosity.
No, I can't even say immediately. It's like not what you're asking for. What is the most non-connected to circuit diagram object that you have?
Yeah, like so. For example, the one reason why I'm interested, right, is because even just representing Clifford algorithms, or is it not? Excuse me, Clifford algebras is something that typically you would have to work in some kind of package for, right? Because there's not like a native representation of some of those mathematical objects, at least not in a way that's easily surfaced. And so I'm curious if people are seeing something here and saying, oh, that's an interesting branch of math that I didn't even realize you could handle in this very concrete computational way. So that's sort of the motivation behind my question there is what are some of the mathematical machinery that goes into finding these stabilizers that people might not even realize that you could do in a concrete computational way, especially in the Wolfram language.
No, I don't know, because the algorithm I'm using here to convert states to stabilizers and operators, they're kind of very, very well known for quite a few decades maybe already. And I'm not even using the most like state-of-the-art ones. So it's just having them all in one framework interconnected with all other objects is pretty nice. So that you can immediately see and like what would be the effect of having one and how they transform and compose with each other. That's kind of, I think it's pretty neat.
Yeah. So you mentioned that currently you had things mostly collected into a super function. What are some other things related to working with the stabilizer formalism that are surfaced that people might find interesting to call as functions?
Well, yeah, one interesting feature is like start with a stabilizer and then add like okay, one of them is this named like the features that we have. A random stabilizer is basically, look at that. It's a random stabilizers. If you convert it into a quantum, the circuit operator, now you would get a random circuit. Okay, so it's like one way of generating random circuit.
It's going to be a random Clifford circuit.
Yeah.
Yeah, this is one way of doing random things. Our idea would be, this is one would generate a random Clifford one, but when you want to generate. This is going to be just like one way of generating random circuits. If you start with the random Clifford one and then sprinkle a bunch of magic operators like T-gates to get just an actual random unitary. That's one idea that we maybe going to explore in the future.
Interesting. Okay, yeah. What are the other built-in things that you can add as arguments to that polystabilizer that people would find of interest?
For example, like,
you have named ones, you can convert your states, operators, circuits back and forth. It's not going to work for all of them. Maybe they fail. You can construct it manually from the actual tableau like this, or the list of generators. I think it's also going to work. Let's try it. Yeah, you can just give it like that. So that just this is like the constructor and the object itself. That's why there's not much other functionality is built in around it. It's just they work together with just by composing and constructing one object from another.
Gotcha. But the input there could be a circuit, could be the list of generators, could be something like random. Okay, good to know.
Yeah.
There's another example. It sounded like you were going to touch on. Did we cover it already?
For example, like, let's have polystabilizer of, like, I don't know, like, 5 qubits, and then let's have, like, I don't know, like, let's have an operation. I don't know, like, Hadamard on, I don't know, like, just
yeah,
one.
you can operate on it.
Yeah. So, like, this is one other neat feature that, like, that all those, like, algebraic features that we have in stabilizer formalism for, like, how the tableau will gonna, like, change due to some operations, like, you can do it here. So, like, the effect there that you see is Hadamard acting on the third, like, qubit, and you see, like, how it changes, like, your stabilizer formalism, and, like, that's the effect of T-gate that creates, like, that superposition. That superposition idea, I feel like, it's a, like, maybe, like, something like original, and it worth exploring more, but, like, we haven't done it yet. One of our to-do lists. But again, like, if anyone, like, graduate students, researchers, like, we are open to collaboration and interact much more on these topics. And, like, the best way, like, maybe we forgot to mention quantum@wolfram.com. So, like, if any question or whenever they want to contact us, quantum@wolfram.com. That's the easiest way of, like, reaching out to us.
And this would be another good time to mention that you also provided at the beginning of the stream a link to a GitHub repository. So you can, in the Packlet repository, you can see code for all sorts of Packlets that are there. You can look locally after you've installed a Packlet, but there's also, in the case of this one and a few other projects that Wolfram works on, there are GitHub repositories where people can submit requests to contribute directly in that way as well. So that's definitely worth mentioning. That, yeah, so let's say that you're thinking about working the stabilizer formalism. This sort of idea of superposition of stabilizers is something that's interesting. You want to directly collaborate, feel free to reach out via those channels, and that could be the start of a very interesting conversation.
And of course, like, we have a big community of, like, users, professional users in our Wolfram community. So, like, that's another venue of, like, interaction. So there they can not only interact with us, but with many other users, like, people, they can share their ideas, they can ask their questions. So, like, Wolfram community is also, like, another way of, like, interacting with Wolfram users.
So we've seen underlying representation you can do as tensor networks. You can represent things using polystabilizers, and in the case of something that doesn't directly admit a representation as a stabilizer, you can sort of look at this superposition of stabilizers, which is quite interesting. So then the other thing, which is a new feature that is also relevant to some of these things that we've been talking about, and it came up once already in the context of exporting to something that doesn't support complex numbers, is this idea of a phase space representation. So this is also something which is new since last year when we've discussed this on a live stream. So let's talk a little bit about phase space representations.
Yeah. Okay. So I guess the entry point to that kind of topic is one other function that we have is called quantum Wigner transform. So people should know that Wigner transformation in usual quantum computation is basically transforming your usual quantum states, wave functions into their phase space, corresponding phase space representation. Here we also implemented or improved, I guess. It did exist for a while, but we improved it on how it actually works and generalizes the same concept for discrete ones, for discrete systems that we're working with, right? So what you can do with the Wigner transform, you can transform quantum states, operators, circuits into one particular representation, or as we're gonna see soon, it's just a basis transform, basically. For example, we already showed you what this double, Mads mentioned this double operation, and what phase space transformation is actually is in relation to that is just this is the same as doubling your operator states circuits like this by increasing your squaring your dimension or thickening your wire, but also then turn them just convert it to a very special unique basis where all your amplitudes become real and can be interpreted as probabilities or quasi-probabilities in general, because sometimes they can actually take negative values. So for example, if you take the state, some random mixed state, two-dimensional one, because it's a two-dimensional state, right? It actually has 1 qubit, but if you transform it, it's going to be 1 4-dimensional qubit now. And as before, while before the Wigner transformation, it just was represented as a density matrix with some complex coherences on the off diagonal. As soon as when you transform it into Wigner basis, all those numbers become real. Like the same quantity of numbers, the same count as the density matrix. So, but they're all going to be real and they also squared and can be treated as probabilities. And you have a bunch of properties that can actually bring these probabilistic properties to the surface more conveniently, rather than just looking at this amplitudes in the special basis here. I don't know, Matt, maybe you want to talk about this more.
So
or
like,
maybe guide me.
There are a few like, details regarding like, the Wigner transform for even and odd dimensions. So let's do some cheating, like, for the time being, let us not mention them. Okay, like, again, like, I'm saying that explicitly, that like, it's a kind of like, cheating, but like, let's not like, get worried about that. So this is basically the Wigner transform. Or one other thing, like, people they can do is like, they can ask for some properties of the, that state. So this is the state in the computational basis. You can ask for is like, phase space. Okay, so like, phase space gives you like, the corresponding representation of the phase space. And for single, like, remember, for only single the qubit systems, when you only have one particle, phase space and quasi probability are the same. Again, like, let's like, for the time being, let's not talk about the difference between quasi probability and phase space. We will comment on that very soon. But let's take any of them, like, phase space, quasi probability for single particle are the same. And what you can do is like, you can do this summation over rows or summation over columns. Okay, like, that's a very like, simple task. And like, so this is a summation over columns, summation over rows, and like, these are basically the quantum probabilities corresponding to the measurement in position, let's call them position, and also like, momentum. So look at here, like, the computational basis, those 0 and 1, let's read them as position, and the other one, like, it's gonna be like basically like, the momentum. And
what made you generate it? It's kind of bad state. It's like probability is always almost the same looking. Oh, this.
Let's just chop them, like, those are like, the precision ones, and yeah, now they're different. So like, you see, like, you see, so like, basically like, it's like, some people they would call it like, the quantum in phase space, like, treating quantum as a sort of like, a statistical mechanic approach. So like, but like, keep that in mind here, like, it's called quasi probability because like, they can also be negative. Look at like, the representation on the top, like, some of the elements are negative. So we won't be worried about like, as you see, like, oh, it's 2 dimension, and if I like measure like in the position space, like why there are 4 results, because like every other one like it's gonna be 0. Okay, so like that's how like it's everything is consistent and it's not gonna cause any issue. Now, everything that you see here is the simple case of 1 qubit in 2 dimension. Remember, like, in our framework, you can go to higher
Do you want to
dimension.
describe how this labeling comes around of the actual, what is the 0 corresponds to if you want to label the actual quasi-probability rows and columns?
Okay, let's discuss about that.
Yeah, because the discrete case is quite a bit more of a headache than the continuous case. Many of you might have seen the continuous case in like a quantum, I don't know what number course, but basically in the continuous case, rather than dealing with the states, you can do a Wigner transform in the continuous case and get something which, again, it's not quite the same as a probability density function, but it's pretty close. And so everything works out. There's some weirdness about, oh, it can go negative, but if you actually compute the things that you would measure, turns out fine. So as you're just saying, the same thing happens in the discrete case, but in the discrete case, there's sort of more things to worry about than in the continuous case.
Yeah. So basically, like, here, what we have is like, the way that you can think about it is like, this transition quasi-probability, like, see it like this. So it's a transition quasi-probability from one point in the phase space to another point. And by definition for us, like, the first, like, block of quadrant of like your quasi probability is for momentum space, and the other ones is for like position. Now look at like that nice table representation that Nick is showing you. In the Wigner transform, you would see only a few elements. Okay, it's only like 4. But when you look at the transition quasi probability, you say, oh, like it's 4 by 4 is like 16. What's going on here? The main reason is like the elements of transition quasi probability, not all of them are independent. There is a nice like algebraic relationship between them. Like it's next time, like we can dive in more into the detail of like phase space, and we can show you all of them. But again, the main reason that Wigner transform has less element compared to quasi probability is because many of those elements have a relationship. There is an algebraic relationship between them. Now, look what we have here. For each element on that table, we can interpret it as a quasi probability of transition from row to column. For example, the first one, which is negative 0.074, 75, 72, this is a transition from x plus to x plus. The second one is going to be x plus to x negative. So it's like, row is like, you go from this state to the other state. So now what's going to happen if I do the summation over all of the, elements in a row? So what I'm going to get all the outgoing amplitudes going out, for example, from the starting point of like, those elements. And as you can see, like, going out from all of them, it gives you basically 0 for those that kind of like, cancel each other. Look at like, the part that Nick is highlighting, you see like, they simply like, cancel each other, because again, like, there is an algebraic relationship.
This is the thing that cancel. Like this is the actual that contribute to your probabilities. This is the probability in your computational basis. Yeah. Because I'm summing over my rows. That's how marginal probabilities in either computational or X basis can be extracted from the transitional quasi probabilities.
Yeah.
It's like, well, if you sum over rows, this part of this table is going to cancel, like because they correspond to, but this part is not going to cancel. If you do it other way around and sum columns instead, you get different set of probabilities that going to correspond not to probability in the computational basis, probabilities of your state, but probabilities in your X basis.
So basically, like, look at like, the first one that we have total. So that total is basically like, it's like adding all the rows, or the different way of saying that is, look at each column, just add up all the elements in each column. So if you add up all the elements in each column, it is as if let's add up all the ingoing quasi probabilities into that very specific point in the phase space. And as you see, for like, if you do it like that for momentum, you will get 0. This is basically the representation of probabilities in position space. If you do it the other way around, you would say, now this time I'm going to add all the elements in a given row. It is basically outgoing to a very specific one, and it corresponds to the probabilities in momentum. Remember, like, the very last line of code that you see here is basically a simple, yeah, that's much better. So like, we totally forgot about like, this transition graph. Let's look at like, labels. Now, like, it's much more clear. Like you get here, like, each of those states, like, there is a, like, edge between them. It represents like, exactly like, those numbers. If you want, like, the adjacency matrix of like, that graph, it gives you exactly like, that quasi probability that you had on the top. Like, those two are like, there's a one-to-one correspondence between them. Some people, they prefer the terminology of like, adjacency matrix. Some people, they like, that visualization of the, like, graph. Like, if you ask me, like, I do not know which one, like, people prefer, but like, both of them, like, they are there. For the simple case of a qubit, the transition graph, it helps. But believe me, like, the moment that you go to higher dimension, that graph becomes so messy, practically, you cannot get anything out of that. But anyhow, like, pick any basically vertex, add up all the amplitudes going into that vertex, or vice versa, like, add up all the amplitudes going out from that vertex. That's how you can get probability in position space, probability in momentum space. Of course, like, you see here, the quasi probability is a square matrix. So you can get only probabilities in position and momentum. If you want to have a sort of like, a variant, you would say, what if I get the one in momentum for particle number 1, and I don't know, like, position for particle number 2. These are like, the moments that you have to go like, to the concept of like, tensors and do like, something, fancier than that. But again, like, here is a single particle, so you don't see the distinction. But okay, let's do it. I know, like, we don't have that much time, but bravely, let's show like,
yes, let's get into it.
Like, a quantum state of like, I don't know, like, random mix, like, here we go, like, 2 by 2, so it's a mixed state. And if we like look how messy it is, but anyhow, you see here, because Nick is asking for full transition graph, now you have a graph and you have the connection between everything. This is basically like, a sort of like, you can also read it as a tensor. Okay, so it's like, this is a graph representation of that particular tensor. Now pick any vertex. If you add up all the probabilities going into that, like, vertex, that's basically like, probability of like, that very particular basis, then out is going to be like, the other one. Remember, like, for whenever we talk about phase space, like, I guess, like, by mistake, I call them probabilities, but remember, they are quasi probability. Okay. Like, many of them, they can be negative. So practically, instead of thinking about like, everything that you can do with the amplitudes and like, I don't know, like, operations, etc., you have this statistical picture of like, your quantum, whatever, your quantum object, your quantum operation. And then you would treat it like a statistical physics of like, your quantum theory, of course, in a discrete space. This is a discrete representation of like, basically Wigner formalism in a continuous case. Then you can have whatever you want, like, like for a circuit, you can have the corresponding like, Wigner transform. And again, like, remember, like, the Wigner transform is literally like, going to a higher dimension. That's why, like, if you look at the diagram is that double diagram. And that's again, like, now maybe like, our users understands like why we have those features and why it's kind of doable in our framework to add phase space formalism, because when you have those tensor concepts behind the scene and tensor network, etc., adding like, these features is going to be like, easy. But if you don't have them, good luck. Like, it's going to be like, really, really difficult, like, to get them done. Let's see, for the phase space, like, I'm thinking about, like, looking at, like, many features that we have, like, which one looks nicer for the representation. Let's see.
Oh yeah, so that's the example that didn't work last time, right? Because I'm forgetting something.
Because it was like, the complex numbers.
Yeah, it's
Yeah, I saw a complex in that sparse array. I'm not sure what the
yeah.
extra step would be.
I'm just trying to understand why it's there. Maybe I'm forgetting something.
So while you're thinking about that, one other question. So as you're discussing before, right? So but by using this Wigner transform, you can think about things in the sort of usual position basis, which is, I think, more the difference between momentum and position, I think, in the continuous case is more straightforward for people to wrap their head around. But so let's say that you want to measure something where effectively you're measuring a momentum in this discrete case. How can you use this Wigner formalism to do that?
So basically, like, it depends, like, if your system, like, remember, like, oh, okay, now, like, so that's basically, like, before
That's what
answering John's question, like,
What was the thing we were forgetting before? So when people are trying this, they know.
Well, I was forgetting this particular thing because by default I get every circuit. When I convert every circuit to tensor network, I convert every operator in it into one computational basis, and so that it's unique across all operators. But when every operator is in the phase space, you don't have to do it. You just take the whatever amplitudes are already computed by transforming it to that phase space representation, and make those tensors your actual tensors into the tensor network that you're going to contract, and those are going to be real. And because now they're real, you can actually contract them using a neural network framework if you want, and maybe do some quantum machine learning in principle. That's what we're building towards here, even with that limitation of absence of complex support, complex number support.
So does the reverse is that functionality also implemented currently, where let's say that you have a net graph and then you've adjusted weights and things like this, can you go back to a circuit, or is that something that will be forthcoming?
Well, in principle, yeah. Well, because net graph, I don't remember. Like, let's see, if this is your net graph. I don't want to recompute it. If this is your net graph, I think that if you can ask for its computational graph. I don't remember what's the property. Do you see some kind of graph in here? Not graphics, but graph. Like maybe this one. Let's see. No, yeah. Let's make a small neural net, smaller circuit, just for Bell state, as an example. Because there's some other kind of limitations. So small net graph. So in principle, this is the graph, right? And we also have a functionality. So if this represents the computational graph of contracting your tensor network, in principle, you can just wrap it with the quantum circuit operator again. I've never tried it actually. So because I have a functionality to turn any kind of graph into the circuit. Let's see what it's going to do. It's going to turn every node in here into some random operator. So it's going to label it with whatever label it was there. Some kind of ugly thing.
Sure.
Yeah. So basically, that's how we go. You can go backwards. Principle.
Nice.
Overall, like, we believe, like, this phase space representation, like, it has lots of potential because, like, it helps you. Basically, that's the entry point of, like, connecting everything quantum with like, you know, more conventional approach that we have in a statistical physics. Like, you know, you can think about like, you know, everything else that we have there, like, you know, and you can apply like, you know, the same here. And I think like, you know, that's one reason that like, you know, for example, many chemists, because, you know, chemists, they have more classical, like, you know, mindset about like, you know, all the processes. Many of them, they prefer like, you know, Wigner representation of like, you know, things rather than like, you know, the usual Schrodinger one, because, you know, when they want to study chemical kinetic, that phase space representation, it's kind of more connected or closer to our like, you know, intuition of what is happening like, you know, in the space. And of course, like, you know, you can have lots of fancy things like, you know, like how X, for example, momentum and position, they are basically literally shifts like, you know, in different direction. It's like shifting your phase space to the right, shifting it down or up, like, you know, we have all those features like, you know. And Wigner is one of those like, you know, things that, you know, we spend time, and its documentation is very detailed. Like, for example, like, you know, we are a bit behind for Pauli stabilizer. So like, you know, we don't have documentation for Pauli stabilizer, but our Wigner transform, it has a very detailed, like, you know, documentation. So people, yeah, that's the one that I'm talking about. Like, you know, look at here, like, you know, when you're applying, like, you know, generalized momentum or position, is like one of them is shifting, like, you know, to the right, like, you know, the other one is shifting, like, you know, down. And that's literally like, you know, the shift operators that we have in phase space.
That's great. And also, especially if you're looking for a nice, easy way to illustrate these things, here we have things which are animated right there in the documentation page, so you don't need to worry about refiguring out how to do that yourself. There's a couple nice examples here.
Yeah.
Another really interesting thing about this Wigner transform in finite dimension is the difference between even and odd dimension. So we may not have time to get too deeply into that this time, but I know that there's a really interesting many things that could be talked about there. So is there anything initially that you want to say about that today?
So basically, like, you know, when the dimension is even, we have to basically double everything for the sake of like, you know, consistency. Like, you know, if you want to treat everything on the same footing, like, you know, you need to, you know, for the even ones, you have to double like, you know, your space. And it's kind of related to that, you know, at the very fundamental level. Remember, like, you know, when dimension is odd, when dimension is even, you know, in one case you have fermions, the other case, like, you know, you have bosons, and like, you know, having a unified, like, you know, formalism, treating all of them in a sense, you know, is related to that. So we could have done two different things. One approach would be treating them completely different, and it was kind of a hacky way of like, you know, treating even and odd. But we decided to have one unified approach, and for that one unified approach, like, you know, we are doubling the space of like, you know, even one. For example, Nick, if you show like, you know, the phase space of, I don't know, the four-dimensional state.
Hold on, I'm lagging a little bit.
So like,
I was
oh, okay.
trying to open some nice pictures and it froze.
So that's an excellent time for the audience. If you have other questions, make sure that they make their way into the chat while we're waiting for a nice picture to load here. Looks like we don't have any other at the moment.
It's because of this maybe animation running independently.
Also, I always notice that Zoom tends to greatly eat my my computer's resources when I'm bringing up high-res stuff.
That's what I wanted to show. The difference in those phase-space topologies for odd versus even dimensions. Basically, odd dimensional systems, if you increase the number of dimensions, like into its continuous limit, definitely the applying of those shift operators, you can now think, because it's going to be always be two-dimensional, so represented by a two-dimensional surface. You can think of the odd dimension as moving this surface of a single donut like this. If you apply a shift operator X or phase shift like this, they're gonna like move around this donut like this. It's gonna be a single one, but for the even case, it's gonna be the only way to represent it nicely. We found that the only thing you can do is have four of those instead, but they're gonna have this negative symmetry to apply to each. So it's like the same kind of size, but each of those has this, instead of a single texture here, it's like in this case, there's only one single bolt on the surface of a donut, right? But in the even dimensional case, each of those have four of those, four copies, but they kind of reflected differently. It's like on one of them, there's a one positive one, but you have negative of this bolt on the other side, right? And you basically all four combination of those represent the whole symmetry of the space symmetry by applying those different shift operators. So that's kind of interesting.
Yeah. So basically, you need like four version, and on purpose, we don't call them like copies, because it's not a copy of the same thing, but like there's a relationship between them. And you see, like since we have four quadrants, if you look at the representation of our Wigner basis, I don't know, like maybe you have it somewhere, Nick, like by convention there is a superscript, and that superscript represents actually these four different like versions, like I guess like we had it somewhere, like yes, you see here, like when it's like the second one, like the top right one, we call it number one, and then we go counterclockwise. Okay, so like it tells you like where in that quadrants like they are located. So, and that's basically the motivation behind the superscript that you see in our Wigner basis.
And each of those four basis elements has a different identification made with what would have been the edges of the manifold, if I understand correctly. In other words, there's a different gluing rule for each of those four basis elements on those tori that you were showing.
Well, in a way, yeah. Basically, each of these quadrants represent those separate four tori. Maybe this picture may be not faithful enough. It actually has to be four different pictures on all of them, but they have this symmetry, because as you can see, this for this simple two-dimensional case, just a single number for each of them, but they're different numbers. So it has to be four different pictures, and if you increase it, the number of dimensions.
If you want, like Nick, scroll up, like I guess like we had like the fully 100% the previous visualization, the other notebook. Yeah, that's basically full 100% like quantum representation of that. So like by the way, this is the very first time that we are explaining that, so we were not sure like that this topology that we explained from the picture of sailing boat, is it more like a better explanation, or the picture of like the actual quasi probability, and break it down into like four quadrants, like which one is better? So our users, you tell us which one is a good explanation.
Yeah, that would actually be a very useful piece of feedback, because I personally am more well studied in the continuous case, and so that spoke to me, but I have no idea about what other people are going to feel about that. So yeah.
So you see, like this the fully quantum version, it tells exactly what we told you. Like they are not actual copies, but there is a relationship between those elements. And in the Wigner like transform, whenever you see, for example, superscript number one, it is top right, and then go counterclockwise, like that's the notation that we have. So that's basically the phase space. But overall, like since we are also like short on time, like let's see, like there's also one question from one of our users. Let me see if I understand. So traditional bits, they have two states, and qubits have four states. What do we speak? Three states. I'm not sure if I understand the question, but if any response, like you can like there is no limitation in terms of like the dimension of your quantum system. Okay, as far as it is finite dimensional, like we have full support. We can have, I don't know, a composite one, like Nick showed you, like we had quantum state, in the state 2 and 3, quantum state, like let's have it in 2, 3, 4, 5, like it doesn't matter. Okay, like, and they can be at any order. Okay, so There's no limitation. So if we skip that, it was just for the sake of like, explanation.
I think the my interpretation of the question has more to do with if you're trying to represent a qubit classically. It takes more classical bits to try to represent a qubit, and so I think the question was, why do you jump from why does it go 2 to the n? That's my interpretation of the question. But yeah, if you want to refine that question a bit, so basically the reason why the 3, if I understand the question correctly, doesn't come up in that conversation is that things are growing 2 to the n in how many classical bits it would take to try to represent something, which is a qubit. So if you're working with a qdit, let's say instead of a qubit, that story would change, and so you can get other numbers in that progression as well.
Well, I think this answer there's going to be a good answer with the stabilizer formalism, when you just can represent classically some states, but not all of them, and it all boils down to the size of your group, the underlying Clifford group, or underlying Clifford plus T group, which is actually quantum versus quantum Clifford plus T, because the groups actually have different sizes.
So one question that some users might have, and I'm also curious, is so when you're thinking about the group theory that goes into this, what computational tools are you using to figure out this group theory? I saw there was something that was a tensor network related function that was to remove cycles, right? And so what are some of the group theory tools that you're using when you're thinking about these things in order to build out this functionality?
I think it's not much. There's not much group theory involved in the in the computational properties of those stabilizers, for example. Just it's very straightforward applying your Pauli operators to a state and see whether they stabilize it or not, something like this. That's like the minimal group theory application. There's no heavy theory involved in there.
And that's what you meant by a greedy algorithm to figure these things out, right? Is you're basically just seeing what commutes, if I understood your answer correctly. Yeah, okay.
The way quantum states is turned into polystabilizer object is kind of stupid right now, but for operators it's a bit better. It's like you can actually use there's like basically 2 ways of doing this. If you can do it directly, there's some very naive algorithm of converting state into a stabilizer, or you can actually convert your state into a circuit, because we have an algorithm for that. And if that circuit can be converted to each individual operators, you can contract it into an operator and convert that. It's going to be maybe less stupid, but it's the same result.
That is the advantage of dealing with finite groups, right? Is that in principle, a computer can just chug through the whole group and see what happens.
Yeah.
So I know that we don't have too much more time left. So if you have other questions, do feel free to put them in chat. So what are some other takeaways that you want people to have if they've caught this stream and they haven't been keeping up with some new developments here that we're adding to the quantum framework? Any other takeaway messages that we want people to have?
I was always install our Packlet from our developer page, because that's the most updated one. Our documentation is updated, so always check the documentation. If any issue, let us know. quantum@wolfram.com. Feel free to reach out to us. And I have one generic comment. Remember, everything that you see here, it is written in Wolfram language. Wolfram language is a functional programming language. So when you're coming to this environment, which is a mathematical notebook, keep that in mind. You need to speak the language of this environment, which is Wolfram language. Okay. It is totally fine. You can write procedural codes. Okay. It's not not that it doesn't work, but if you code in a procedural way in Wolfram language, oh gosh, you're going to suffer a lot. Okay. So you would not appreciate the neat features that this functional programming language has. And by the way, Nick is sharing the notebook, so if you just take a picture, you can see the notebook immediately. So it's like, the example that we discussed, like, it's going to a country, so learn the native languages spoken in that country. Okay. You are in, like, mathematical notebook. So try to write down your codes in a functional way. Because if you don't do that, like, as I told you, you would not see, like, how powerful it is. Nick, what do you think? Any advice you have for our users?
Just contribute. I want more contribution. So if you have an opportunity to do it, please do. It's like right now, just I'm the only one who just developing the functionality, but I would highly appreciate any help or like in any direction of quantum computation.
Yeah, and I mean, the lowest hanging fruit there, right, is that so if there's some named circuit, right, where there's a common thing that you might want to do, and you see it's not added to the list of named circuits that have that automatic support, but I mean, you can build it using gates explicitly, and you can check out some either documentation or some of our previous YouTube conversations about how you can do that. One very low-hanging fruit way to contribute would be if there's a named circuit that you're interested in, feel free to implement that, and that would be a really interesting and nice way to contribute. So I don't see any other user questions at the moment. So that's good. Hopefully that means that we've answered the ones that people have currently. And remember, so when you're dealing with the quantum framework, because you can handle either symbolic objects or numerical objects, these are handled differently in Wolfram language. So if you want to have things be numbers that have some machine precision, you can do that and sometimes be able to go through a computation faster because numerical methods can sometimes be faster. But if you want to handle things symbolically and get an exact result so that you're not computing just some approximation to the theoretical result and then comparing it to what you're getting on quantum hardware, but you want to see the actual exact thing with symbolic parameters and everything, you can handle both sorts of things. So because the Wolfram language has support for both of these paradigms of working with representing mathematical objects, you can do the same thing in the quantum framework too. So that's worth mentioning, is that another thing to learn how it's handled if you're wanting to use this framework is that square root of 1 over square root of 2 is a different thing in its underlying representation than that numerical thing that you're seeing by calling n there, right? I mean, in many circumstances it doesn't quite matter which one you're using, but in this language they really are genuinely different things, and so you can do different things with them. Okay. So still not seeing any other new user questions coming in. So again, thanks all very much for joining us today. If you have not been keeping up with some of the new functionality, remember, you can install directly the developer version if you want to get the absolutely latest and greatest, even before they show up in the Packlet repository version. You can represent things as tensor networks, which is something that we didn't talk about too much last time. The stabilizer formalism has been added more recently, which is quite exciting. And the Wigner transform is another way of thinking about how do you represent quantum systems that has some interesting applications, and definitely looking forward to having a future conversation about Wigner transforms, because as we're just getting into at the end, there's some exciting ways that you can try to explain to people, okay, what's the deal with this Wigner transform?
Thank you, John. Thank you, Nick.
Thanks, John. Thanks, Matt.
And thanks for joining us.